Okay, let's continue. So, what we've seen in the last slide. Welcome back. To start with, of course, what we've seen in the last slide was that we can define a notion of entailment based on the question whether the models of the formula that we want to see entailed are a superset of the models of all the knowledge base of our knowledge base. So it's a very simple notion relating the truth of a sentence with respect to knowledge base to the relation between models and validity of these models with respect to the sentences and the knowledge base. Based on this notion of entailment, or the relation of models, we can define other notions that are sort of semantically interesting. This was the one that we've seen. So a sentence alpha is entailed by a knowledge base if alpha holds or is true in all the models of the knowledge base. In other words, if the knowledge base, the models for the knowledge base is a subset of the models for the formula alpha. So it's another way of looking at it. A sentence is valid if it is true in all the models. So that was my example here that I showed you with the formula that was true whatever way we chose our variable x, whatever value we chose for x. So the simple formula in the arithmetic logic was valid according to this definition of validity. And in propositional logic, we have these examples here that if A or not A, then it doesn't really matter how you choose A, whether A is true or false, the formula here will always be true. If you choose A to be true, then the first one will be true. If you chose to be false, the second one will be true. So the formula itself will be true. So no matter how you choose your variable, your propositional variable, the value of the propositional value, you will always get the value true for the entire formula. And there are more examples of those that can become rather complicated. If we have variables and if we have some of the models that satisfy the formula and some of them don't, we have the notion of satisfiability. If there is a model which makes the formula true. So in this sense, if A or B, there is a model. If we choose either A or B to be true, then this would satisfy this formula. So then this formula is satisfiable. So A is true, B is false would be a model. A is true, B is true would be a model. B is true, A is false would be a model. Only A is false, B is false would not be a model. But the formula is satisfiable. There are also formulas that are not satisfiable. So the formula A and not A is unsatisfiable because no matter what we choose for A to be the value, if we interpreted it, it will evaluate this formula to be false. So if A is false, then it would be false and true, which is false. And if A was interpreted to be false, then we would have false and true, which is false again. And I think I gave the same explanation twice, but I think you got the general message. Yeah? So how does it look formally? We would assign values to the propositions. So a proposition is, in this case, P12, which if we look at the Wumpers world, so this is an example from the Wumpers world, we would say there is a pit in 1-2 in this specific interpretation of the world of Wumpers that we're in. We assign so to each of the propositional variables either true or false. That gives us an interpretation, and if this interpretation is consistent with respect to all the axioms in the knowledge base, then it would be a model of the knowledge base. But the notion of truth and satisfying an axiom is sort of given by assigning values to the atoms and then extending it to the complex operation. So a formula not S is interpreted to be true if the formula S is interpreted to be false. So it's a recursive definition. We first give the definition for the atoms in the language, and then basically we give we extend the notion of truth to the of satisfying an axiom to the complex formulas in our language. So S1 and S2 is true if S1 is true and S2 is true, and so forth. And that allows us in a simple recursive process to assign a value to a complex formula depending on the choice of axioms, atoms, the value for the atoms. So P12 was supposed to be true, so the negation of it, P12 was supposed to be, so I'm confused here because I think it must have been sort of the opposite of this assignment that we use here to evaluate this formula. So if P12 is false, then it is interpreted, the negation of it is interpreted to be true. And so don't be confused. It's not this assignment that we have on the top, but sort of the inverse of it. So that's a problem with this example. But then you can basically roll out the truth value of your complex formula by the atomic values. And later we will use also some kind of rewriting, and because we want to translate this semantic notion into algorithms, we will use these kind of rules that you can see are valid according to entailed by are valid in propositional logic. So whenever you have a formula which says alpha implies beta, you can also write down not beta implies alpha, not alpha, which is always true. So it's a valid formula, and we can use those valid formula for rewriting processes. So that's quite useful. So we can turn this semantic notion into an algorithmic notion, and this is what happens here. Okay, so if you now go to the breathing and the pits of of our Wumpus world again, then you can see that we can now use these formalisms to model the information that is needed to do the entailment. So how would you do it? You would write Pi is true if there is a pit in the square Ij. Bij is true if there is a breeze in Ij. And then the situation that we have had would be modeled as there is a breeze in 2.1, there is no breeze in 1.1, and there is no pit in 1.1 because otherwise the game would not have even started. So this is the game information that we start out with, and then we have the rules of the game. And the rules of the game are that if there is a breeze in 1.1, then we know that there is a pit either in 1.2 or in 2.1. And we would need to write these down for all the 1-2s. So because we are in propositional logic, we see already this sort of creates some kind of problems. We would also have to write for 2-1 that on top, onto the left, onto the right, there must be somewhere a pit. And this is the first stops to model that a square is breezy if and only if there is an adjacent pit. And as we are in a very inexpressive language, we have to do this. We have to write this down for all the squares one by one. So if we would write down all the rules for this 4x4 game, we would have a lot of axioms to write down. Yeah? But still, this is already good enough, because now we can derive with this information that Pit 2.1, this is information we need, is equivalent to either P1 or P2 or P3, and then we can have some additional information about the P11, which is false, so we have P22 or P31. So that already gives us more information about where the pit would be. Yeah? So this is a way of representing the knowledge of the Wumpus world in propositional logic. The good news is propositional logic is declarative, so you write it down in a way that's easily understandable for humans. You can write part of the information, so you don't need full information. You can write down whatever you learn, and maybe you cannot derive the full information from it, but at least you can derive some facts already. It's compositional. That's another nice tool. So if you have partial information, you can derive the meaning from each of the individual parts of it. And it's context independent, so you don't need to understand more about the statements. You can just interpret the statements and derive the facts that you need for your game. But it has, as we have already seen on the last slide, it has very limited expressive powers. So in the game here, we need to write down that a square is breezy if only if there is an adjacent pit. For all of the squares, so 16 times, we need to write it down for all the squares around. And that's really sort of annoying. I will come back on those words tomorrow, because in a way it is also very powerful. It's very nice. But for the modeling side, it's really rather painful. So you cannot say pits cause breezes in adjacent squares. That would be a very nice thing to write down once in one statement, and then you're done. And this leads us to first order logic. So a logic where we can do this, where we can quantify over all the different states in our system. And that's the language I want to spend the last half hour on. Language that you might be less familiar with. But I want to make a point, something that I really want to spend more time on tomorrow, is how would you represent the knowledge about Schnapsen in propositional logic or in first order logic. And I've already done the step now to lift this to first order logic, where I basically say a trump wedding is anything where I do have the queen, and the queen is trump, and there exists some thing with the same color, which is the king, and it's in my cards. It's my set of cards. Yeah? So basically what I want to say is I know which cards I have, and I want to qualitatively model that the king of the same color is in my hands. Yeah? And this is one way of doing this. And if I would write that down for all the cards, it would be rather painful. So this is what I really want to write down. This is one strategy which I want to apply, where I say if I have the queen of a trump wedding, I always play it first. That might be a strategy that you want to play. And this would be a way of writing it down in a logical statement. So now I only would have to check, do I have a card? For every card that I have in my hand, I need to apply my reasoner and ask, is it a trump wedding card? And if it says yes, it is, then I should play it. If it says no, it isn't, then I shouldn't play it. In order to be able to do this, I need to model things like same color. So when do two cards have the same color? What is the value of the different cards, and so forth. So this would be things I would like to model. And I can do this in propositional logic, and we will get back to this tomorrow and on Wednesday. But the more elegant and the more sort of natural way of doing this is to use the language of first order logic. I believe that you all saw first order logic in logic and sets at the end. So you moved from the propositional logic to the first order logic. But I also guess that your first order logic modeling skills will be a bit rusty. So I want to spend the last 20 minutes on sort of repeating the formalisms about the language. And I want to spend tomorrow in a more interactive way of trying to see whether we can come up with some strategies and model them in the language, so that we really can enrich our agents, our logical agents, playing Schnapsen with real human strategy, and to see how this works in this language. So, whereas the propositional logic, as I said, looks at the world and sees whether things are true or false, propositions are as facts of the world. First order logic tries more to model the world as it is. So it tries to talk about objects, it tries to talk about the relations between objects and values that can be assigned to those objects. So in other words, objects are things like people, houses, numbers, colors, as you wish. And the relations between that, either unary relations, so predicates, so a house can be red, a ball can be round, a number can be prime, but also relating to objects of the domain. So a person can be the brother of someone, or a number can be bigger than something. So we talk about both the objects of the domain and relations between those objects. And then we can have a function which assigns one value in a domain to an object. So that gives us a far more powerful language to play around with and to model our information with than the propositional logic. These are the basic elements. We have constants, so some persons, some numbers, some institutions. We have relations between those objects. We have such as being the brother of someone or being bigger than, and we have functions that take an object and assign a value to it. So the square root or the left leg of an object, a person or something like this. We also allow for variables, as we had in our arithmetic example. We allow for equality, and there's some notion of quantification where we can talk about all possible objects of a certain class or a certain domain, or we can assume the existence of a specific one. You're all aware of that, so the universal quantifier, the existential quantifier are these elements, so you shouldn't, if you haven't seen those, then you have forgotten quite a lot in your study. So these are elements that you should refamiliarize yourself. I will actually, in the reader, the chapter on first order logic is not included. I will add that. I think we have it. I will also add it to the reading material. Because in principle, the examples that I give and the explanation that I do really comes out of this book. And is I think, quite nice to just read it, and you will sort of hopefully understand the ideas better. So again, as we did in propositional logic, we first have to think of the kind of legal sentences that we can write down. And basically, we have the notion of atomic sentences. And these atomic sentences, they are just consist of predicates that I can apply to some term. So a term would then refer to an object in the domain, and the predicates relate those objects or give them properties. And the terms themselves, there would just be some constants or some variables, or there would be function terms that could be either applied on one option or on one object or two objects or more objects. So let's look at some examples. That would be an atomic sentence would be the brother of King John would be Richard Lionheart, or I think it's the other way around. No, it's not the other way around, sorry. It's the brother relation, so it's symmetric. Where this would be a predicate, and this would just be a constant term in my language. This would also be a constant term in my language. So this would be a legal sentence, legal sentence in my language. This would also be one where I have a function that says, give me from Richard, the constant, give me the length of give me the left leg of this person. So that would assign an object to this statement. It would assign to this object, it would assign a value from the domain of natural numbers probably, or rational numbers through the length function. And then we could compare two of those terms, the length of the left leg from King John and the length of the left leg of Richard, by some bigger than operator. So that would be a predicate bigger than applied to two terms, where each of the terms is a function applied on a term. So that's the syntax of these atomic statements. And then I can build complex sentences from those atomic statements by simply adding the same operators that we had in propositional logic, namely the negation, the conjunction, the disjunction, the implication, and the equivalence. And here are some more examples on this. This would be an atomic term, and I would just have an implication. So if sibling King John Richard, then Richard King John are also siblings. Or I can build complex formulas. This would be either 1 is smaller than 2 or 1 is smaller or equal than 2. So that would also be a valid formula. And to these sentences, then, you would apply some notion of model theory again, where we define sentences via truth of interpretations to make them models. So models contain objects and relations among them, and they interpret them according to the specifications of the knowledge base in which they are written down. So we map what is it now? We map constants to objects in our domain and relations to relations in the domain between those, and then we map the functions to functions, or function symbols to functions, and we map sentences to truth values in the end. So in principle, the idea is very similar, but now we have more mappings not only to the domain of true and false, but we first have a sort of mapping to a concrete universe where we have relations between objects that we then evaluate the truth on. So you can think of a model in first-order logic as some kind of graph where you have an object which has a label. So this would be the object Richard, and it belongs to it has a property of being a person. It has a part. There's a function between these two things which gives you one object. So the red things would be functions. And the blue things would be properties of them, so predicates, and there are relations between two objects that you can also model. So in a way, we move away from the simple notion of truth or falsity of sentences to, first of all, we have a universe of objects, and these objects are related, and then the question is whether these properties hold or not, and that gives us a notion of truth on which we define our notion of validity and entailment again. And then you have the next step, and that is the two elements that we haven't discussed yet, is the universal quantification and the existential quantification. So we have a variable that is preceded by this universal quantifiers, and then we have a sentence, and the variables are then applied on the variables with the same name in the sentence. So, for example, you have the for all x here, and then the x has a range of this x and this x. Sometimes you need parentheses, but in a way, if you don't have an ambiguity, then you just don't leave out the parentheses, the brackets. And this basically means that for all the things that if they are at the US government, then they are smart. Yeah. So whenever you encounter an object that has the property of being a relation between X and the object US government by and works at or whatever interpret here, then you also know that it has the property being smart. And the definition of this is that for all X, P is true in a model, M if P is true with X being each possible object in the model. So you have to sort of evaluate all the X's in the domain to make things true. And this is an interesting point where we sort of step from the propositional case to the first order case, where we overstep a little bit, because basically this applies to all the objects in the domain. So when we want to quantify over all the 16 squares in our Wumpus world, then we know that the domain are these 16 objects. Yeah? So we have 16 times, we have to check 16 times all this information, but we know that it is restricted to these 16 elements. Whereas if we model it in first order logic, it's about all possible interpretations of these variables. And so how is the formalism supposed to know that there are only these 16 objects? So in the propositional logic case, we have a very redundant way of writing things down, because we can write down about each of the objects and we have all the information. But the first order case is a bit bigger, because we can't sort of restrict it to know that there are only these 16 objects. And that is a price very high to pay in terms of reasoning. We'll see that on one of these days, tomorrow on Wednesday. But in practical terms now, for the modeling side, the only thing we have to understand is that P of x is true if it's true with all the interpretations of the x possible. Yeah? And then the whole formula becomes true. So in a way, it is roughly speaking equivalent to the conjunction of the instantiations of P. And this is what we're going to use later for our reasoning. So I promise that this comes back on Wednesday. So basically, if you have all your objects X working at the US government being smart, you just have to write it for all the object that you have. So King John works at the US government, so he'll be smart. Richard works at the US government, he'll be smart. And you write it down for all the objects, so you have to write it down for the US government as well. So if the US government works for the US government, it's smart as well. So now we've sort of reduced the meaning of this universally quantified formula to a propositional one. There is a common mistake. So the main connective with this universal quantification is the implication. So basically, that's how I wrote it down here. So basically, if you are X, a member of the US government, then you will be smart. If you write down by mistake for all X is US government and smart, then basically you state something else, and definitely not what you want to say, because then you state that everyone works for the US government and is smart. So it seems a trivial mistake, but it's really one that's easy to make. So make sure you normally use, when you model something, you use implication with universal quantification. The other operator that's sort of typical for first order logic is existential quantification, when you want to refer to one possible value in your interpretation without knowing which value it is. So here you would say someone at the US government is smart. You don't know who it is, but there is someone. You want to say, in the Wumpus world, you would say there must be a world where the Wumpus is, because this is part of the rule. So you could say the Wumpus is in 1.1, or in 1.2, or in 1.3, or in 1.4, or in 2.1, and so forth. You enlist all the 14, so it's a disjunction of the possibilities. Or in first order logic, you just say there exists an IJ where the Wumpus is. And you're done. You have written down the one statement. Yeah? So there exists an X. P is true in a model, M, if P is true with X being some possible object to make P true. And it basically gives you the disjunction of the thing. So either King John is smart, or Richard is smart, or the US government itself is smart, so that could also be an option in this propositionalization. Basically, that's a difference I explained with saying, okay, the Wumpus is either here, or here, or here, or here, or saying there exists a world in which the Wumpus must be. That is exactly the same thing here. As with with universal quantification, where if you use the conjunction, you have to be careful. You might have a similar problem here if you do the existential quantification, and if you use the implication, you also don't say what you really want to say, because if you say there exists something or someone, if he works for the US government, then he's smart. This formula is already true if someone doesn't work at the US government, then the statement is already true. because this is sort of the fallacy of the first order logic, or the logic in general, that if you have something that's false, everything's implied. So this is also not what you want. So make sure that whenever you use an existential quantification, the natural thing to do is to apply the conjunction. So there are some properties, and you just check them out. I'm sure you've seen them, but they are quite useful to remember when you really do some actual modeling with them in practice. So you can turn around the quantifier. So if you say for all x, for all y, you can also write down for all y, for all x, and the same for the existential quantifiers. The order doesn't matter. The order matters if you mix existential quantification and universal quantification. So the exist in x for all y is not the same as to say for all y they exist in x. So here is an example for this. The exist in x for all y loves x. Y means there is a person who loves everyone in the world. So there's one person with, so sounds a bit like God to me, but so this would state this statement here, and the other one, everyone in the world is loved by at least one person. So that's the example to show that these are not the same, yeah, because these two statements have a completely different meaning. Whether we give all our love to one person, or we get all love from one person, or whether we have our specific person we get our love from, I think that's a very, very different thing. And then there's this duality of quantifiers. So in principle, we would only need one of the quantifiers. So for everybody, for all x likes x ice cream, so everybody likes ice cream. It also means there doesn't exist anybody who does not like ice cream. It's exactly the same meaning. So we could rewrite for all x likes x ice cream by not exists, not likes ice cream. And the same is the other way around. There exists someone who likes broccoli. Doesn't mean not everybody dislikes broccoli. So that is the rewriting of those. Yeah, so it's the same, it means the same thing. And for reasoning purposes, that's quite handy to have, as we will see later. So if you look at this example with with King John or whatever, then the kind of things you can write down with first order logic are for all xy, brother xy implies that sibling is xi. So whenever you are related to someone in a brother relation, you're also related in a sibling relation. You can define the notion of a mother. So a mother of C is a mother if C is a mother of M if M is female, and they are in a parent relation. You can also have more and more higher properties such as symmetry. So whenever you choose an xy, and x and y are in a sibling relation, y and x are also in a sibling relation. Which is not true for all the relations, of course, because the mother relation would not be symmetric. So if x and y would be in the mother relation, it would not mean that they are in the mother relation the other way around, of course. And it's a very powerful framework, so you can also define set theory in this first order logic. So I won't bore you with the details, but the first one says, for example, that for everything that is a set, the property is that it's either an empty set or it has been constructed by some set plus an extra element. So that's, I think, one of the Zermelo-Fraenkel axioms. And you can go on like this. So there doesn't exist an empty set that has been constructed by a set and adding some axiom, some element. So if you're interested, you can go through the list. But this is sort of the first order representation of a set theory. And then you can look at the Wondrous world, which obviously was the motivation for us to do this. So you can, this is if you look at it from an agent perspective, it's important to translate your perceptions to some actions in the logical language. So if you perceive somewhere that you are in a state with a breeze and you perceive a glitter, then you know that there is you can translate your perceptions into some state of the world, namely that at time point t there is a glitter at a certain state, and then you can also define your rules, your reflexes. If you're a reflex action, for example, but just stating that whenever you encounter a glitter, then the best action to do is to grab and get the goal that is there. So here you can translate your perceptions and your into actions using the logical framework. And we will simplify this a little bit because we sort of it creates a little bit of overhead. I think we'll do that more informally, but the idea is exactly the same. In Schnapsen, you will have a kind of rule where you say, if this is a suitable card, play it. That's basically what's going on here. And obviously the nice thing is that you can deduce now these unknown, these hidden properties. You can infer over your knowledge so that you find out whether a place is safe or not. And here you, for example, can define a notion of adjacency by, a place XY is adjacent to a place AB if AB is defined as x plus y, so above it, and the y is the same, or below, or y is to the left and y is to the right. So these would be the four options to define. And this is one way of sort of writing down what in propositional logic would be really a pain to write down. Then you can have properties of agents. So if an agent is at a certain point, a certain state, and there is a breeze in it, then the state has a certain property. You can use it for diagnostics and so forth. So I mean, I think you understand the power of this reasoning capability in this kind of game because we looked at it from the intuitive perspective. So how are we going to apply this now to our own Go game? On purposes, we have to identify the task. We have to look at the task very, very carefully. What is it we want to achieve with our task? And what is then the knowledge about the game, the knowledge about the strategy that we want to apply? How do we write this down in logical terms? What are the predicates with the function and the constant? So if we, for example, want a strategy in which we want to apply the knowledge of how many points we have and our opponents have, then we probably need a different function than if we leave this information out. So we need to make our choices there. And then it's encoding the general knowledge about the domain. What is it? What are the terms that we want to use? Look at the specific problems. What are the 5 cards in my hand? And then turn this into an inference procedure and get the answer of, should we make this move? Should we play this card or shouldn't we? And this is what we're going to do tomorrow. So on Wednesday, and this is where this becomes a little bit bizarre, a bit strange, so a bit getting used to it. I said propositional logic wasn't expressive enough, so we needed first order logic. So we are modeling in first order logic, but as we will see, reasoning in first order logic is too big, is too expressive, is too much. So when we now want to do the reasoning with the models that we're going to build tomorrow, we need to sort of translate them automatically back to propositional logic. So we make a detour. We use a knowledge representation language of first order logic because it's very intuitive to reason. But in the end, we go back to we use the first order logic because it's very elegant to represent the knowledge, but when we do the automatic reasoning, we move back to the more simple formalism. And this is a good example of what the kind of research that I do is about how can we find the right representation language for the right problem. And here we sort of make a move towards a good language for modeling, and then we're going to see that tomorrow. And then we're looking for a language that is very good for reasoning, and we will see that on Wednesday how that works. So tomorrow, let's try to look at this in more detail. So how can we find first order representations of the games so that we can model useful strategies and implement them in our agents during this week. Enjoy the rest of the day and see you tomorrow.